Hello and welcome to part 3 of our lecture 6 in Math 2R03. In this part of the lecture, I'm going to be looking at looking at kind of one theorem and spending most of my time proving this particular theorem. In this theorem, it says that if you have a finite dimensional vector space, every list of linearly independent vectors is less than or equal to the length of every spanning list of vectors. Okay, so if you may not totally grasp what this is saying, here's another way to think about it. Suppose that somebody gives you a collection of linearly independent vectors in your vector space, and they also give you a list of vectors v1 through vn that span v. So completely different people could give you this information. And what the theorem is saying is, if somebody gives you a list that spans v, and somebody gives you a list that's linear independent in v, that m, the number of linear independent vectors, will have to be less than or equal to the number of vectors that the person who gave you that gave you of a list of vectors that spanned v. And so any linear independent list and any list that spans, you have this relationship m is less than or equal to n. So that's what we're going to prove. And let me make some more room on the screen. Here we go. And we're going to work out all the details. Okay. So first we start with the fact that v1 through vm span v. That's one of our hypotheses. So now take the u1 and throw it to the front of your list. So you have u1, v1 to vm. You get that this is a linearly dependent list. And then why was that true? Well, you know that a1 v1 up to an vn has to be equal to u1 for some ai's, right? For some a1 up to an, because u1 is in v, so it's in the span. But then you can rearrange, so you have that minus 1 times u1 plus a1 v1 up to an vn equals 0. Right? And this is a linear dependence among the vector because we've found a non-trivial solution to write the 0 vector. Okay, now we just proved something about linearly dependent vectors. And what we proved is that we can remove, when you take u1, v1, and so on, you can remove one of them from the list. Okay, and you still have a set that still spans v. Okay, so you can remove one. You would normally keep u1, and then you would throw away one of the ones from v1 through vn. So the new list of u1 and m minus 1 of v1 up to vm. Oh, sorry, that should be a vn, excuse me. And this should be n minus 1. And u1 and n minus 1 of v1 through vm is a list that spans v. Okay, so we have a linear dependence. u1 isn't going to go away because u1 is a single vector, it's a non-zero vector, so that it's not linearly dependent when we start. And then we add the v1, and then we add the v2, and then we add the v3. At some point we'll find a vi that can be written in terms of the smaller guys. So that's why we were getting rid of a v. Okay, so now we repeat the process. At the j step, all right, so far we found j minus 1 of the ui's in my list, and I have m minus j minus 1 vectors from my original lab. So what I've been doing in each step is I'm removing a vi and I throw in a ui. Okay, so that's what I'm kind of doing. And each time the linearly dependent lemma allows me to do is throw something out, put something in, and then throw something out, and I don't destroy the spanning part. And so uj, which is another vector because it's inside of v, is inside of here. But that means that uj is a linear combination of those guys. So that means that when you take u1, uj, and then you put the uj in your list, and then you take the rest of the guys, you get that it's linearly dependent. Okay, because these guys span all of it. So one of these, you can write uj in terms of the linear combinations of those. Okay, so you have a linearly dependent. And then what happens is, since you know that u1, u2 up to uj are linearly independent, okay, when we remove an element, we remove one of the VIs, right? Because the way the linear independence lemma says is, okay, look at the first guy, then look at the second guy. Is it in the span or not? Now, because the UIs are all linearly independent, right? When we add each of the UIs, it's not going to show up in any of the earlier linear combinations of the UIs. It's only when you get to the V's that you could probably write the V's in terms of what comes earlier. So you're removing one of the VIs. So what ends up happening is that at the next step, you have something like this. So you remove one of the VIs and you put in the UJs. So you have that U1 up to UJ, and then V, and we don't actually know what all these indices are, right? So we'll just write it as K sub 1, V K sub 2, up to V K sub J, and there are M minus J of these guys spans V. Okay, so they span V. And what we're doing is at each step, we remove one VI, we remove one VI, and add one UJ. And at every step, we're able to remove one VI and add a UJ. So that means you have at least as many UJs as you do VIs, right? But the number of UJs is N, and the number, the number of UJs is M, and the number of VIs is M. So we have that M is less than or equal to N. Okay, so whenever we have VI, whenever we have a VI, make sure I say it in the right order. Whenever we have a VI, we can throw it out and replace it with a UI. So at the end, we can take each of these VIs and we put it with a UI. So that means each of we have at least, if we have M UIs, then we have to have at least M VIs because each of them are getting replaced at each step. So we end up with M less than or equal to N. Okay. It's a bit of a complicated proof. Take a look at the textbook and hopefully my notes here will help you. Just kind of as a consequence here is you get a result that we proved in linear algebra in a special case, which is if you take the set of all n tuples Fn, no list of P greater than n vectors is linearly independent. So this is the idea is if you took 4 vectors in R3, then it has to be linearly dependent. Okay, and why is that? We know that 1, 0, 0, 0, 1, 0, up to 0, 0, 0, 1 spans Fn. This is something that we proved in the last lecture. So any linearly independent list of vectors is less than or equal to n. Okay, and I just want to point out that this is something actually we did prove this result in 1B03, but we used the language of like pivots of a matrix. And so here we have this result and we haven't even talked about what a matrix is, and we're still able to prove this consequence using what we've just done. Okay, so we'll take a pause here and then we'll kind of finish up with some kind of other results about finite dimensional vector spaces.